This slide presents the overview of the chapter.
Learning objectives. By the end of this chapter, you will be able to identify rational and irrational numbers, state fundamental theorem of arithmetic, explain decimal expansions, prove irrational numbers, state laws of logarithms.
Introduction. Before entering into the chapter, follow the instructions shown on the screen. Click each tab to know more.
We learned from previous classes that natural numbers are the set of numbers which start from 1. They are denoted by n. Example: n is equal to 1, 2, 3, so on. Whole numbers are the set of numbers that include 0 along with the natural numbers. They are denoted by W. Example: 0, 1, 2, 3, and so on. An integer is a whole number that can be positive or negative or 0, but it should not be a fractional number. It is denoted by letter Z. For example, Z is equal to -3, -2, -1, 0, 1, 2, 3, and so on. Now, let us recall about rational and irrational numbers. Rational numbers are the numbers that can be expressed in the form of p by q, where p and q are integers and q not equal to 0. They are denoted by q. Always, rational numbers are expressed by using terminating decimals or non-terminating repeating decimals. Examples of rational numbers are as shown on the screen. Finally, we conclude that rational numbers contain the set of natural numbers, whole numbers, and integers. We also have irrational numbers which cannot be expressed in the form of p by q, where p, q are integers and q not equal to 0. Some of these numbers are √2, √3, and mathematical quantities like pi. When these are written as decimals, they are non-terminating and non-recurring. You know that rational numbers contain the set of natural numbers, whole numbers, and integers. But do you know that rational numbers are contained in some other set of numbers? Let us learn about various properties of rational and irrational numbers in details, and also about logarithms. Let us know about Euclid's division algorithm. The algorithm name itself suggests us to do with divisibility of integers. It simply states that if any positive integer x is divided by another positive integer y, then it gives remainder z which is smaller than y. Let us do an example. Suppose if x is equal to 22, y is equal to 5, then the remainder z equal to 2, which is smaller than y. The result obtained by division process is quite easy to understand, but it has got many applications relating to divisibility properties of integers. Let us learn few of them which are mainly used to calculate HCF of two positive integers. Now, let us learn about Euclid's division lemma by considering a puzzle. A trader was moving along a road by selling cups. An idler who did not have much work to do started to get the trader into a wordy duel. This grew into a fight. He pulled the basket with cups and dashed it on the floor. The cups broke. The trader requested the panchayat to ask the idler to pay for the broken cups. The panchayat asked the trader how many cups were broken. He gave the following response. If counted in pairs, 1 will remain. If counted in threes, 2 will remain. If counted in fours, 3 will remain. If counted in fives, 4 will remain. If counted in sixes, 5 will remain. If counted in sevens, nothing will remain. My basket cannot accommodate more than 150 cups. How many cups were there? Let us try to solve the puzzle and find how many cups were there in the basket. Solution. Let the number of cups be A. From the given problem, if we observe it from the last, we can say that A less than or equal to 150. Since the basket can accommodate either 150 cups or less than 150 cups, but not more than that. 1. If A is divided by 2, 3, 4, 5, 6 each time, then we know that the remainder in each case is 1 less than the divisor. That is, A is 1 less than the LCM of 2, 3, 4, 5, 6. Now LCM of 2, 3, 4, 5, 6 is 60. Therefore, A can be 60 minus 1, 120 minus 1, 180 minus 1, and so on. 2. If A is divided by 7, nothing will left given. That is, A is divisible by 7. 60 minus 1, that is 59, is not divisible by 7. 120 minus 1, that is 119, is divisible by 7. Therefore, A can be 119. 3. The trader basket cannot accommodate more than 150 cups. Therefore, 180 minus 1 cups cannot be there. Therefore, number of cups broken is equal to 119. To understand the Euclid's division lemma more clearly, let us do the problem by considering following pair of integers. A. 28. B. 17, 5. Consider a bit that is 20 and 8. Here A is equal to 20, B is equal to 8. Thus, by applying the Euclid's division lemma EDL to the above numbers, we obtain as follows. Here we know that A is equal to BQ plus R. So when 20 is divided by 8, we obtain quotient Q as 2 and remainder R is equal to 4. Substituting the obtained values of Q and R in the above expression, we obtain both LHS and RHS equal. Similarly, let's consider second set of numbers 17 and 5. Here, A is equal to 17, B is equal to 5. Thus, by applying the Euclid's division lemma EDL to the above numbers, we obtain as follows. Here we know that A is equal to BQ plus R. So when 17 is divided by 5, we obtain quotient Q as 3 and remainder R is equal to 2. Substituting the obtained values of Q and R in the above expression, we obtain both LHS and RHS equal. Sir, in Euclid's division lemma, the term lemma sounds differently. I never heard about it. Lemma is the typical word to hear and pronounce, but it is just a result. It is used in proving the other theorems. Suppose one wants to compute the HCF of two numbers, the most common method used is factorization. But to compute the factorization of large numbers, such as 65,842, 24,895 and so on, is very difficult and takes a lot of time. So Euclid has came up with a theorem that would help us to find the factorization method easily in less time. This theorem is very simple and is just another form of divisibility rule, which we have studied in our lower classes. Sir, could you please explain us the theorem of Euclid's? Okay, listen to the theorem statement. Now, let us know theorem on Euclid's division lemma. Statement: if a and b are two positive integers, then there exists unique whole number q and r, such that a is equal to bq plus r, where 0 less than or equal to r is less than b. Do you remember the divisibility theorem? Dividend is equal to divisor into quotient plus remainder. The Euclid's division theorem is originated from this. Sir, but how is it possible to use this theorem to find HCF? Can you please explain us more clearly in simpler way by taking few examples? To understand more clearly, first let me explain the theorem by an algorithm, step-by-step manner and flowchart. Algorithm. An algorithm is a step-by-step procedure or formula for solving a problem. The word algorithm has come from the name of the Persian mathematician Al-Khwarizmi, earlier transliterated as algorithm or algorithm. The word algebra is also derived from a book which he has written called Hisab al-Jabr wal-Muqabala. Euclid's division algorithm is used to compute the highest common factor, HCF, of two given positive integers. To obtain the HCF of two positive numbers, say a and b, follow these steps. Step 1. Apply Euclid's division lemma to a and b, so there exists whole numbers p and r, such that a is equal to bp plus r, where 0 less than or less than b. Step 2. If r equal to 0, b is the HCF of a and b. If r is not equal to 0, then apply division of lemma to b and r. Step 3. Continue the same process until the remainder is 0. The divisor that is obtained at this stage is the required HCF. Flowchart. Here let us know sequentially in the flowchart to keep the steps to find the HCF. Let the first number be a and second number be b. If a is greater than b, then according to Euclid's division, lemma a is equal to bq plus r, where q and r integers and 0 less than or equal to or less than b. Suppose a is equal to bq plus r. If r is equal to 0, then b is the HCF of positive numbers a and b. If a is equal to bq plus r, if r not equal to 0, we apply the division lemma to b and r and continue the process till the remainder becomes 0. If a is less than b, then according to Euclid's division, lemma b is equal to aq plus r, where q and r are integers and 0 less than or equal to r less than a. In b is equal to aq plus r. If r is equal to 0, then a is the HCF of positive numbers a and b. In b is equal to aq plus r. If r is not equal to 0, we apply the division lemma to a and r and continue the process till the remainder becomes 0. Now, let us do some examples by taking small numbers first and then large numbers. To understand the Euclid's division lemma more clearly, let us find the HCF by considering following pairs of integers. A. 24. Step 1. Apply EDL to the above numbers. Here A is equal to 20, B is equal to 4. Substitute the values in A is equal to BQ plus R. So when 20 is divided by 4, we obtain quotient Q as 5 and remainder R is equal to 0. Substituting the obtained values of Q and R in the above expression, we obtain both LHS and RHS equal. That is 20 is equal to 4 into 5 plus 0. As the remainder is 0, the process stops. The divisor at this stage is 4. Therefore, HCF is equal to 4. B. 4032, 262. In the given pair, 4032 is greater than 262. Therefore, let A is equal to 4032 and B is equal to 262. Step 1. By applying EDL relation A equal to BQ plus R, where 0 less than or equal to B less than R, we get as shown. So, 4032 is equal to 262 into 15 plus 102. As R equal to 102, which is in turn not equal to 0. Now apply Euclid's division lemma to 262 and 102. Step 2. (262) is equal to 102 into 2 plus 58. As R is equal to 58, which is not equal to 0. Apply Euclid's division lemma to 102 and 58. Step 3. (102) is equal to 58 into 1 plus 44. As R is equal to 44, which is not equal to 0. Apply Euclid's division lemma to 58 and 44. Step 4. Here 58 is equal to 44 into 1 plus 14. As R equal to 14, it is not equal to 0. Apply Euclid's division lemma to 44 and 14. Step 5. (44) is equal to 14 into 3 plus 2. As R equal to 2, it is not equal to 0. Apply Euclid's division lemma to 14 and 2. Step 6. (14) is equal to 2 into 7 plus 0. Since the remainder is 0, the process stops. The divisor at this stage is 2. Hence, HCF is equal to 2. Euclid's division lemma or algorithm has several applications in order to find the properties of numbers. Let us do some examples. Show that every positive even integer is of the form 2q and every positive odd integer is of the form 2q plus 1, where q is some integer. Solution. Let a be any positive integer and b is equal to 2. By Euclid's algorithm, a is equal to 2q plus r for some integer q greater than or equal to 0 and or equal to 0 or equal to 1. 1. For or equal to 0. A is equal to 2q. 2. For or equal to 1. A is equal to 2q plus 1. If A is of the form 2q, then A is an even integer. If A is of the form 2q plus 1, then A can be any positive odd integer. Two. Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integer. Solution. Let a be any positive integer and b equal to 6. By substituting the value of b in EDL a equal to bq plus r, we get a equal to 6q plus r, where 0 less than or equal to or less than 6. Now, by substituting or equal to 0 in equation 1, we obtain a equal to 6q. By substituting or equal to 1 in equation 1, we obtain a equal to 6q plus 1. By substituting or equal to 2 in equation 1, we obtain a equal to 6q plus 2. By substituting or equal to 3 in equation 1, we obtain a equal to 6q plus 3. By substituting or equal to 4 in equation 1, we obtain a equal to 6q plus 4. By substituting or equal to 5 in equation 1, we obtain a equal to 6q plus 5. Solving the above equations for a, we obtain a is equal to 6q or 6q plus 1 or 6q plus 2 or 6q plus 3 or 6q plus 4 or 6q plus 5. From equation 2, 6q, 6q plus 2, 6q plus 4 are the even integers. 6q plus 1, 6q plus 3, 6q plus 5 are the forms of any positive odd integer. Verification. Assume any value of q such as 1, 2, 3, 4, so on up to n. Substituting the values of q in equation 2.2, we get, if q equal to 1, then 6q plus 1 is equal to 6 into 1 plus 1, which is equal to 6 plus 1, that is 7, which is a positive odd integer. 6q plus 3 is equal to 6 into 1 plus 3, which is in turn equal to 6 plus 3, that is 9, which is a positive odd integer. 6q plus 5 is equal to 6 into 1 plus 5, which is in turn equal to 6 plus 5, that is 11, which is a positive odd integer. If q equal to 2, then 6q plus 1 is equal to 6 into 2 plus 1, which is in turn equal to 12 plus 1, that is 13, which is a positive odd integer. 6q plus 3 is equal to 6 into 2 plus 3, which is in turn equal to 12 plus 3, that is 15, which is a positive odd integer. 6q plus 5 is equal to 6 into 2 plus 5, which is in turn equal to 12 plus 5, that is 17, which is a positive odd integer. Similarly, for different values of q, we obtain the result as a positive odd integer. Problem 3 is that use Euclid's division lemma to show the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Solution. Let a be any positive integer and b equal to 3. Substituting the value of b in Euclid's division lemma a equal to b cube plus r, we get a is equal to 3 cube plus r, where 0 less than or equal to or less than 3. Let it be equation 1. Case 1. If r equal to 0, then a equal to 3 cube, that is equation 1.1. By cubing equation 1.1 on both sides, we get a cube is equal to 3q cube, which is equal to a cube equal to 27q cube. That is in turn equal to a cube equal to 9 into 3q cube. That a cube is equal to 9m, where m equal to 3q cube, that is equation 1.1.1. Case 2. If r equal to 1, then a is equal to 3q plus 1. By cubing equation 1.2 on both sides, we get a cube is equal to 3q plus 1 whole cube. As it is in the form of a plus b whole cube, we write it as shown. Now, by further solving, we get a cube is equal to 9m plus 1. Let us represent it as equation 1.2.1, where m is equal to 3q cube plus 3q square plus q. Case 3. If r equal to 2, then a is equal to 3q plus 2. By cubing equation 1.3 on both sides, we get a cube equal to 3q plus 2 whole cube. As it is in the form of a plus b whole cube, we write it as shown. Now, by further solving, we get a cube is equal to 9m plus 8. Let us represent it as equation 1.3.1, where m is equal to 3q cube plus 6q square plus 4q. Thus, from the obtained result in 3 cases, we can say that the cube of any positive integer will be of the form 9m, 9m plus 1, 9m plus 8. (4) Show that the square of any positive integer is either of the form 4m, 4m plus 1 for some integer m. Solution. Let a be any positive integer and b is equal to 4. By substituting the value of b in Euclid's division, we obtain a is equal to 4q plus r, where 0 is less than or equal t or less than 4. The possible reminders are r equal to 0, 1, 2, 3. Case 1 for r equal to 0. A is equal to 4q plus 0, that is a equal to 4q. By squaring equation 1.1 on both sides, we obtain a square is equal to 16q square is equal to 4q square. This is in the form of 4m, where m is equal to 4q square. Case 2 for r equal to 1. A is equal to 4q plus 1. By squaring equation 1.2 on both sides, we obtain a square is equal to 4q plus 1 whole square, which is equal to 16q square plus 8q plus 1, which is in turn equal to 4 into 4q square plus 2 plus 1. This is in the form of 4m plus 1, where m is equal to 4q square plus 2. Case 3. For r equal to 2, a is equal to 4q plus 2. By squaring equation 1.3 on both sides, we obtain a square is equal to 4q plus 2 whole square, that is equal to 16q square plus 16q plus 4, which is in turn equal to 4 into 4q square plus 4q plus 1. This is in the form of 4m. Let it be represented as equation 1.3.1. Case 4. For r equal to 3, a is equal to 4q plus 3. By squaring equation 1.4 on both sides, we obtain a square is equal to 4q plus 3 whole square, which is in turn equal to 16q square plus 24q plus 9, which is equal to 4 into 4q square plus 6q plus 2 plus 1. This is in the form of 4m plus 1. Let it be represented as 1.4.1. Exercise problem. Let us solve exercise problem. You can click Solution tab to verify your answer.
Let us solve a few exercise problems. Click the tab to view solution.
Let us see a discussion between Raju and Rajesh about real numbers. Rajesh, are all integers also included in real numbers? Why?